Hello and welcome to this video for Chem 20. In this video, we are going to look at the type of different forces of attractions that can happen between molecules. Okay, so we know within a molecule, we have ionic and covalent bonds, but what's happening between neighboring molecules? So for example, if I were to take water and if I were to fill water up above the surface level of a glass, it would actually not spill over because the water molecules are acting like magnets and they're all being held together. So there's an attractive force between them, and there are actually three types of attractive forces that are found between molecular compounds depending on some of the properties of those molecular compounds that we'll talk about. Now, before we get into those, we do have to talk about a special type of compounds called a network solid. A network solid is basically very similar to the crystal lattice structure that an ionic compound takes on. However, it happens in specific molecular compounds where this is what they look like. But essentially, it's a 3D array of covalent bonds between the atoms that are very, very, very strong. Some of the strongest out of all of the forces of attraction that we'll talk about. Some examples are diamond and silicon carbide. They have really high melting points, and they are very hard. They're not malleable or ductile because they have fixed bond angles. So this is what they look like. So the examples are diamond, which is carbon that's been compressed under a huge amount of pressure, silicon carbide, and silicon dioxide. Okay, those are the three. Just memorize, if you have one of these three compounds, they're the strongest possible compounds. What you're going to be asked to do a little bit later on in the unit is to order your compounds by their boiling points. And so by their boiling points, you want to think of the forces of attraction. The higher the forces of attraction, the higher its boiling point. So if your compound has diamond, silicon carbide, or silicon dioxide, it has these network covalent bonds, making them have the highest boiling point of everything. Okay, so this is an example of diamonds. All the carbon atoms are bonded with these covalent bonds between them. So they look similar to the crystal lattice structures we talked about with ionic compounds. But in ionic compounds, they were ionic bonds between them. Here, these are all covalent bonds. And covalent bonds are actually much stronger than ionic bonds. Okay, so here's another one showing silicon dioxide, all the covalent bonds between them, making a really strong network, making these have the highest boiling point out of all the molecules that we'll talk about. Okay, so just memorize those three. So the type of forces that we're going to talk about today, so far we've been talking about intramolecular forces. These mean forces of attraction within a molecule. So within a molecule, if I'm looking at water, it's referring to the covalent bonds, the bonds that are holding the hydrogens and the oxygens together. But like I mentioned, water molecules also have another type of attraction between them called intermolecular forces. This is the force of attraction between molecules. So if I have another water molecule, there's an attractive force between them. This water molecule with this water molecule. And that's what the intermolecular force is. And there's three of them that we'll talk about. London dispersion, dipole-dipole, and hydrogen bonding. For short, we write LD for London dispersion, DD for dipole-dipole, and HB for hydrogen bonding. Okay, really quickly, I can tell you how to identify them. All molecular compounds have London dispersion, and I'll explain what they are in a minute. If the molecule is polar, they have also dipole-dipole. And then if the molecule has H bonded to N, O, or F, it also has hydrogen bonding. So the molecule will either have only London dispersion, which all molecular compounds do. If it's polar, it'll have London dispersion and dipole-dipole. And then if it has hydrogen bonded directly to N, O, or F, it'll have what's called hydrogen bonding, as well as the dipole-dipole and the London dispersion. So either one, two, or all three of the intermolecular forces. So that's how you identify them. You could technically stop this video now and go through your molecules and identify all of the forces present in your molecules. But we will go through the notes and go through what they are and why they happen. So they are considered weak forces compared to ionic bonds and covalent bonds, but they are responsible for melting points and boiling points. And like I said, you're going to be asked to order molecules by their boiling points. And the way you're going to do that is by looking at what forces they have. The more forces, the higher the boiling point. So DD first, dipole-dipole. So as I mentioned, dipole-dipole is found in all polar molecules. So if your molecule is polar, the whole molecule, not the individual bonds, but if the overall molecule is polar, it will have dipole-dipole. And the reason this happens is because the slightly positive end of one molecule is being attracted to the slightly negative end of another molecule. Just like opposite charges, they attract. If they have like charges, they repel, but when they have opposite charges, they attract. So they align themselves so that their opposite charges can attract, and that makes them hold together kind of like glue, and that's what gives them higher surface tension, higher viscosity, and so on. Okay, hydrogen bonding, as I said, HB for short, is when hydrogen is bonded to N, O, or F, NOF. Hydrogen has to be bonded to one of those three elements. Okay, it is a special type of dipole-dipole interaction that is very strong. So it's a special type of interaction between a positive and negative charge. That's what dipole-dipole means, the slight positive end and the slight negative end. And the reason it happens with hydrogen with only these three elements are very highly electronegative. Okay, oxygen, fluorine, and nitrogen, they have the highest electronegativity of everything, which means when the hydrogen is sharing electrons with these three elements are pulling so hard that they almost fully pull the hydrogen's electrons away. So that means the hydrogen becomes essentially just an exposed proton because its nucleus has a proton with no neutrons, and if it's losing the one electron that it's trying to share, it basically becomes what we call an exposed proton. So this hydrogen proton then gets attracted to the negative pole of the neighboring atoms, but also the lone pair of the neighboring atoms, because nitrogen, oxygen, and fluorine always have lone pairs, right? Hydrogen has two lone pairs, nitrogen has one lone pair, those are the two on oxygen. Fluorine has three lone pairs. So if that's my hydrogen there, bonded to my fluorine, it has three lone pairs, okay? So within the molecule, the H has to be bonded to N, O, or F, but the hydrogen bond is actually between two neighboring molecules. So the H of one molecule to the F of another molecule, all right? So hydrogen bonding happens if H in the molecule is directly bonded to N, O, or F. You have to actually draw the molecule to see if it's bonded. Because if you were given something like CH3F, you might think there's H and F, so there's hydrogen bonding. But if you draw it, the F is actually bonded only to the C, and the H's are only bonded to the C. So there is no hydrogen bonding here, because again, it needs to be N, O, or F that the H is bonded to, not C. Okay? And then lastly, London dispersion, LD for short, are found in all molecular compounds. All of these forces, London dispersion, dipole-dipole, and hydrogen bonding, are only found in molecular compounds, not ionic. Ionic compounds just take on the crystal lattice structure, and that's it. Okay? Molecular compounds have London dispersion, dipole-dipole, and hydrogen bonding. At least London dispersion, if not two or three of them. So the reason London dispersion forces exist is it's just essentially a very weak dipole-dipole attraction between what we call induced dipoles. Okay? So because electrons are in constant random motion, there will be a brief instance where the distribution of electrons is distorted, which causes the molecule to become polar for a moment. Okay? Slightly polar, polar for a brief moment. That produces dipoles, positive, slightly positive, and slightly negative ends again. And so because of these dipoles, it actually causes like a flickering effect to the other ones. And as they all become slightly polar, they can then attract like dipole-dipole does, where the slight positive end attracts to the slight negative end. But because these molecules are not permanently polar, they're only temporarily polar, that's why it's weaker than dipole-dipole, because dipole-dipole is present all the time. These only happen for brief moments and then go away. However, like I said, for some substances, this is the only force of intermolecular attraction that they have. So they can play a role on what's happening. So there's two factors that affect the strength of the London dispersion forces. One is the number of electrons. The more electrons, the stronger the London dispersion, because the more often they'll become polarized or slightly polar. As well, the surface area, the amount of contact between the molecules. So if you have a big molecule, like let's say I have C4H10, there's lots of surface area on this molecule. This drawn as a structural diagram looks like this, but there's really electron clouds around them, right? So that has a lot more surface area than something like HCl. So this would have stronger London dispersion forces than the HCl would, okay? When we're talking here also about the number of electrons, this is the total electrons, not just valence electrons. So to find it, let's say you have CH4, you're going to add up the atomic number of everything. That's how many electrons they have. So carbon's atomic number is 6, and hydrogen is 1, and there's 4 of them. So the total number of electrons that CH4 has is 10. If you compare that to something else, right, something that had 12 electrons or 14, or they could even have 100 and something, the more the electrons, the stronger the London dispersion. Okay? So here is showing you this, a visual of the three forces. So London dispersion is happening in all molecules. It is the only force if your molecule is nonpolar. And it's because the molecule becomes slightly or temporarily polar. And it's an attractive force between two neighboring molecules that are nonpolar. If they're polar, they also have dipole-dipole because it's a permanent polar molecule. So there's a permanent attraction between the slight positive and slight negative end of two neighboring molecules. If it also has hydrogen bonding, then it has an H again bonded to N or F, and it's becoming almost a complete positive and complete negative. So it's an extremely polar molecule. So there's a degree of polarity increasing as you go from London dispersion to hydrogen bonding. So in London dispersion, they're only temporarily polar. Dipole-dipole, they're always polar. Hydrogen bonding are extremely polar. So there's the difference between the positive and negative end is getting bigger and bigger and bigger. Okay, so more stronger forces of attraction. Now, if we were to put all of these forces of attraction that we talked about on a scale, London dispersion and dipole-dipole are pretty equal. London dispersion is a little bit less than dipole-dipole. Hydrogen bonding is higher than them. But these three that make up the intermolecular forces are at the low end of the scale. The intramolecular forces are higher. Okay, metallic, there's a wide range, so we don't put it on the chart, but they would be higher than molecular compounds. Ionic bonds are kind of in the middle. Covalent bonds are a little bit stronger. And then the network covalent, remember those three compounds we talked about, diamond, silicon carbide, and silicon dioxide, they have the highest force of attraction between them. Okay. Now, this force of attraction chart is important to notice because this is what impacts our order of boiling point. These are the forces that we break when we boil a molecular compound. Boil or melt, whatever we're doing, anytime there's a phase change with a molecular compound, we are not breaking the covalent bonds. These do not break when you have a phase change. only the London dispersion, dipole-dipole, and hydrogen bonds break. Okay, so that's why ionic compounds have a higher boiling points than molecular, and network covalent are the highest. Okay, so network covalent are the highest, then ionic, then molecular at the end, but the more forces of attraction they have, the higher their boiling point will be. Okay, so in summary, if you're asked to identify intramolecular forces, it wants to know, is it ionic or covalent? So it's ionic if it's an ionic compound, covalent if it's a molecular compound. Then it wants to know what intermolecular forces they have. If they're ionic, they have none. If they're molecular, you have to draw them out to check if they're polar or not, check if they have hydrogen bonding or not. So my CH4 is nonpolar, so it has London dispersion only. There's no dipole-dipole, and there's no hydrogen bonding because H is bonded to C, not NO or F. CH3OH, on the other hand, would look like this. It is polar because my central atom carbon is bonded to 3 hydrogens and then an oxygen. So that breaks its ability to cancel polarity. So not only is it London dispersion, it's also dipole-dipole because it's polar. And then on top of that, it has a hydrogen bonded to an oxygen, which is what's needed for hydrogen bonding. So CH3OH has all 3 forces. Okay, so this was, again, the intramolecular. This was the intermolecular. So in your assignment, you are going to identify, again, which forces of attraction are present in your compounds. If they're ionic, they have no intermolecular forces. If they're molecular, they are either London dispersion and dipole-dipole, or London dispersion, dipole-dipole, and hydrogen bonding. If you go back to the beginning of the video again, there's a summary of, again, how to identify which forces are present in your molecular compounds. The last thing that we'll look at is order of boiling points. So using the scale of forces, you can order the compounds based on their relative boiling points. What you want to think of is, what are the intramolecular forces? So is it ionic or molecular or network covalent? Step 2, what are the intermolecular forces? So the London dispersion, dipole-dipole, and hydrogen bonding. If those are the same, then look at how many electrons there are in total between the 2 compounds if you're trying to order their boiling points. And if those are the same, then look at the overall size of the compound, the surface area of the compound. So for example, from highest to lowest, you will have in a list, let's say you have 1, 2, 3, 4, 5, 6 compounds. Okay, 4 of them are molecular, 1 of them is network covalent, and 1 of them is ionic. The one that is network covalent, again, is going to be the highest. The one that is ionic is the next highest. The molecular are all at the bottom. But again, the more forces they have, the higher they are. So the molecular with all 3 is the highest. The molecular with only 2 is the next highest. And then you'll probably be left with 2 that have the same force. Then you look at, like I said, the number of electrons, and whichever one has more electrons is stronger or a higher boiling point, or which one has a bigger surface area. Whichever one has a bigger surface area is then higher or have a higher boiling point. Okay, so this is your scale of forces, being able to order compounds by their relative. You don't have to know what their boiling points are, but you can order their relative boiling points by using this chart. So that is it for this lesson. Thank you for watching this video.